All right, we are starting Unit 5, and we are actually in for a bit of a treat today and over the next couple of days. Today, we're taking a step back and not really doing any calculus, like no derivatives or anything like that. We need to learn about um, sort of a special area of logarithms that we don't talk about in MHF. And like I said, it's pretty special. So we're going to talk about that today, introducing this one new idea. And you can see our learning goal is, I guess, kind of silly, but I can do a whole lot of things with exponents and logarithms. So the other thing we're doing today is just reviewing everything that we know, or not everything that we know, but a whole bunch of stuff that we know about logarithms. Um, that's going to be important because we just learned about logarithms in advanced functions, and it's brand new. And if you remember back then, it's tricky because it happens at the end of the year, and people are busy with other stuff, and they end up maybe not spending the time on that unit like they should. And even though logarithms are fairly straightforward, some people, it doesn't click for them, and they don't see a lot of success in that unit. And if that was you, then you're maybe not starting from the greatest position in terms of coming into this unit. That's okay. We're going to take a day to look at this. I would recommend, if today's not enough, to go back and review all the other stuff. The properties and just the general nature of a logarithm is going to be really important. So keep that in mind. Um, but as always, when we're talking about calculus, we do have a different approach with all of this stuff than we did in MHF and advanced functions. Um, so that's what we're doing today. Like I said, just reviewing all of a bunch of properties and different things about logarithms to get back into it. I wanted to say when you first learn it, the analogy that I give is it's like learning a new language, and there's nothing intuitive necessarily about a new language because it just is the way that it is, and it can seem very different from possibly the language that you're used to. And so we have to be careful using our intuition when we're learning a new language, and we have to kind of there's things we have to just memorize, we have to just experience, and we just have to have enough time, spend enough time with it, in order to start to become comfortable with it and start to really speak that language. Okay, so keep that in mind, and it's kind of similar in this case of calculus and doing logarithms, except that we're not going to have as much time to go over all these details. So hopefully you will be able to get refreshed and caught up with just kind of looking at reviewing the stuff that we need to review. All right, let's get started. Um, First thing we're going to do is look at the graph of logarithms and exponential graphs. And we are going to do a bit of sketching in this unit. So keep that in mind. When we do the sketching, having an understanding of these graphs will be paramount. I'll give you a little bit of an advance notice on this, just that it'll be things like end behavior and asymptotes. Finding those in these kinds of graphs will rely on our knowledge of these base graphs. Okay, so even though we didn't do a lot of graphing of logarithms in MHF, you need to know the basic shape, and you need to know its basic behavior, and you need to know where its asymptote is. Okay, um, but it's not going to help us too much today. In MHF, we used it for restrictions, for kind of understanding restrictions, that kind of thing, and it can be helpful for that. And there will be that in this unit as well. As always, when we're taking a derivative, we are often setting it equal to 0 and solving. And when you're solving a logarithmic equation, you're going to have restrictions. But we're not getting there just yet. We will do a little bit of solving, but really, I think knowing these graphs is going to pay off for when we do sketching later on. Okay, so first of all, if I just look at this green graph here, can I figure out what it is, what function it actually is? And it's an exponential function, and exponential functions without transformations always go through 1 because, don't write this down yet, y equals 2 to the 0 or 3 to the 0 or 4 to the 0 are all 1, right? So when you raise any exponent to 0, any base to an exponent of 0, you get 1. So that doesn't help us, but it does maybe tell us that there's no transformations. These are just the base graphs, so there aren't any. And then the next one, if I was doing a table of values, so at x equals 1, or sorry, at x equals 0, y is 1. That doesn't tell us anything. At x equals 1, y looks like 10. Okay. And that means this is a graph of y equals 10 to the x. So at 2, it's going to be at 100, which is way off the graph. And this is something that hopefully we remember, hopefully we know. It is, they grow really fast, right? So even just getting up to 2 would go off the graph and would be too big for us to plot. Generally speaking, we might think of this as the graph of y equals b to the x. Some base b, and it's y equals whatever the base is to the exponent of x. That's what makes it an exponential function. In this specific case, my b is 10, right? And it's y equals 10 to the x. You can have any base, and that's going to change your function. But there is something that all exponential functions, regardless of base, that they share, sort of a nature that they share, and that's important for us to know. Okay, this red graph is the inverse of the other one, and we learned what inverse means, and so this one is going to be y equals log, base b of x. In this case, the base is 10, so it would be y equals log base 10 of x, or y equals log of x, because remember, here's our review of this part of the language of logarithms. When it's just log, it means base 10. Okay, that's just our standard. If there's no base written, it means base 10. If it's any other base, then you're going to have to write it. Okay, those are the inverse of each other. Again, look at the asymptotes. Logs have an asymptote at at x equals 0, and exponential functions, the base function, has an asymptote at y equals 0. And like I said, that will be important for sketching and a little bit of solving and stuff that we do later on. Okay, so that's a quick review of exponential functions, the graph of exponential functions, and the graph of logarithmic functions. So I've got another one here. Why do I have this one? We sort of by inspection determined the first one, the exponential function, was y equals 10 to the x. So what does this one look like? Again, it looks like it goes through 1 there, so there's no transformation. So I might look at where does it go through when x equals 1, what is the y value? And it's right here, okay? And I can, whoops, that wasn't very straight, follow it over. And what exactly does it look like to you? It's more than 2, it's less than 3, it's more than 2.5. What would be your guess? What would you estimate it to be? Okay, so I don't actually expect you to guess what it is exactly. It is more than 2.6. In fact, it's a bit more than 2.7. It's less than 2.8. That's hard to tell from the graph. It is actually approximately 2.718 or 2.72 to the x. Okay, why in the world is this a graph on our on this lesson? Why is this random number the base of this graph? Well, before I get into it, it's not a coincidence. Obviously, there's a reason. I said that we are learning one very important thing in this lesson, introducing a whole new big important part of mathematics, and it has to do with this graph right here. Before I get to that, in logarithms, we have the standard, like we often use log base 10, right? And there's good reasons for that. We didn't really get into them in MHF. For us, it was almost just that's the button our calculator uses. Um, and you could use other bases as well, but base 10 is a common one. And other bases might be convenient for particular questions, but base 10 is a common one. Well, this is the other common base that we see. And before I get too much more into it, I want to throw a question out there. If I said, name the most important numbers that you know of in all of mathematics, what would you list? Okay, make a list, a short list of important numbers, numbers that have unique properties, maybe numbers that are important in a different way from just random numbers, I suppose. What would they be? If you want to pause the video for a second and think about that, it might be a great idea. Okay, so I hope maybe you would come up with numbers like pi. How's that? What do you think about pi? Okay, important numbers. Often people say I. If you think about that, I is when we introduce the idea of imaginary numbers. We start talking about I, and it's kind of the fundamental starting point of imaginary numbers. If you watched any videos about imaginary numbers explaining how they're not actually imaginary, you would see how unbelievably important the number I is. Some people might say the golden ratio, phi or phi, people pronounce it differently. That's one of the most important numbers. I'm not going to list it here, but in some ways, in some areas of mathematics, it is very true that it's an interesting number and an important number. Other important numbers that you might have come up with, I hope, 0. Why is 0 important? Well, because if I add by 0, I don't change the thing that I'm adding to. That's the only number that you can add to something and it doesn't change it, right? And when we complete the square, we see how important that is. I can't divide by 0. I can divide by other numbers. I can't divide by 0. If I multiply by 0, I always get 0, right? It's the only number that really works that way. So there's important things to 0, and it comes up a lot. The 0 product property allows us to solve polynomial equations and other equations, rational equations, inequalities, all kinds of things, right? 0 is where intercepts happen. Like 0, I think clearly when you start thinking about this stuff that way, is an important number. You might have thought of another one very close to 0, the number 1 is also important. To get common denominators and fractions, we multiply by a convenient one when we're rationalizing denominators, or often when we use conjugates, we're multiplying by 1, the conjugate over itself, right? So 1 is a very important number. When we multiply by 1, it doesn't change the thing that we're talking about, or divide by 1, it doesn't change the thing that we're dividing by 1. So 1 is another really important number in all of mathematics. You might also say 10 because it's the base for our number system, but even if you had a number system with a different base, these numbers would still be important, but 10 wouldn't. If you had a number system, if you were working in a number system that, let's say, is base 2 binary, then these could all still be important numbers, whereas 10 wouldn't really be as important, okay? So in our number system, because it's base 10, sure, 10 is important, but not to the same level as these. And these are probably very arguably the 4 most important numbers in all of mathematics. And well, today we're learning about the 5th one, which is called E. And that is this number. So this is actually a graph of y equals e to the x, where e is approximately 2.71828 dot or approximately 2.72, as I said before. And it is irrational like pi. It goes on forever, never repeats, never ends. Um, and it is arguably, I mean, different people who work in different areas of mathematics are probably going to disagree maybe, but is arguably one of the 5 most important numbers in all of mathematics, okay? And so it's kind of a big deal, and we're learning about that today. And I'm going to talk a little bit about the history of this thing because it's super interesting, but I'm not going to get too much into it because it's complicated for one, and we could talk about it for a long, long time, and that's not what this is about. But if you're interested in learning more about this, I would encourage you to read up about this and try to understand it, because some of the applications of this are they're accessible, things that you can understand, and they're interesting. Um, so I think it could be worth reading if you're interested in that sort of thing. So before I move on, this is the green graph here is the graph of y equals e to the x. So it's still exponential, where e is this irrational number, okay? That's approximately 2.72. And this is the graph of y equals log base e of x. Just like I rearrange this 10 to the x and log base 10 of x, or log of x. Same thing, if this graph is y equals e to the x, its inverse is y equals log base e of x. Now, the number e is so important to exponential growth and to logarithms that, in fact, it has a totally different notation and a totally different name, and it's called ln. Okay, so it's ln, and we pronounce it ln, y equals ln of x. So ln means log base e. And from now on, that's how we're going to talk about it. I'll remind you if you need it, but you'll get used to it quickly. So if I just say log of x, I mean log base 10. If I say ln of x, I mean log base e. So it's not a different operation than logarithms. It is a logarithm. It's just got the special base of e. Okay. Um, now, I'm going to talk a little bit about the history of e because I think it's really interesting. There was a famous mathematician, and many of you probably haven't heard of him. His first name was Leonard, and that's his last name. It looks like Euler or something like that, but it's actually pronounced Euler. So if you ever hear of Leonard Euler, that's who we're talking about right now. Brilliant, brilliant mathematician. Some people might say the most brilliant ever. So prolific, and by that I mean he accomplished so much and he had so many proofs that people started attributing his proofs to other people who weren't the first to prove them. Often if you're the first to prove something, it gets named after you or something like that. But Euler had so many important proofs that they couldn't name anymore after him. So they started just naming them after other people who worked with him or who worked on the problem as well, or who did something else with the problem afterwards, or whatever, because they just couldn't keep naming things after him. So that's how prolific he was. That's how much stuff that he came up with on his own. And he was brilliant, brilliant, brilliant. Now, there is something called Euler's formula. I'm not going to do Euler's formula right now. It has to do with some trigonometry, and we wouldn't quite understand it, although it wouldn't be too far off for you to understand with a little bit of talking or reading. But we're not going to do that right now. I'm going to show you a special case of Euler's formula called Euler's identity, and it goes something like this. E to the exponent I times pi plus 1 equals 0. You could do this on your calculator. In fact, let me see if this will work for me. You may have noticed that your calculator has a button for E, so Shift E, look at that, it's right in there. Shift E to the, now I got to find my I button because I haven't used that very much. Hopefully I can find it. Oh dear, I might have to do this later. In fact, oh my gosh, I don't see it, and you probably do see it. Okay, hold on. I'm going to see if this works. I haven't actually tested this, so let's see. I is the square root of -1, so let's see if that works. Times pi plus 1. I'll actually be a little bit surprised if this works, but let's see. Okay, math error, it didn't work. I'm going to play around with that. I'm going to try it on my physical calculator and see if I can get it to work there. I'm not entirely surprised that didn't work. At any rate, you'll have to take my word for it that this is true. This is called Euler's identity. You can look it up easily, or if you look up Euler's formula, this is a special case of that. And just soak that in for a minute. What's going on in this identity, in this statement? Remember when I said what are probably, very arguably, most people would agree, a lot of people would agree, the 5 most important numbers in all of mathematics. And look at this. They are related in a way that couldn't be more simple. There's not a squared in here. There's not any other number in here. There's nothing else going on. There's exponentiation. There's an exponent. You're raising something to an exponent. We're adding, and we've got an equal sign because it's an identity. But that's it. There is nothing else going on here. This is incredible that the 5 most important numbers in all of mathematics could be related in such a simple way. In fact, Euler thought that this was so perfect. Allegedly, I've heard, I don't know if this is true, but this is the story that I've heard, that to him this was a proof that God exists. Um, Now, I don't know about that. Lots of mathematicians, lots of very brilliant people can be a little quirky and can sometimes have some sort of strange beliefs. And who knows everybody's background and their beliefs. But for Euler, who was a brilliant person, there was something divine about this. Okay. At any rate, it is absolutely, regardless of your beliefs, it is absolutely astounding that this is true and that those 5 important numbers can be related in such a simple way. Now, there's a little bit of trickery going on here because I could rearrange this to look like that, in which case it doesn't have a 1 at all. It's got a -1 and it doesn't have a 0, right? But regardless, it's pretty amazing. The other thing I want to say about E, Euler was not the person who discovered it. The person who discovered it, or actually, they don't know that he discovered it, but he had done calculations based on it. So the first place where this is sort of seen in print, in publishing, was from someone who had made calculations using the number E, but never mentioned the number E, certainly didn't call it E. It wasn't called E back then. I think a few decades later, it was published by somebody else. And then 100 years later, I think something like that, my remembering of the dates might be off, Euler started using it, and it was Euler who termed it E, and that stuck. But Euler was not the person who invented it. And here's it's not known why it's E. Did he name it after himself? It's certainly possible, although I'm not sure he was known to be pretentious or self-absorbed that way. It could be that it has to do with exponents, and so he used E because of exponents. It could be that he was doing a lot of work with other constants, and I can't remember what the other constant was, but he used A for it, and E is the next vowel. So some people have said he was probably just using vowels as variables or in place of his constants, and A was already taken, so we went to the next one that was E. So nobody knows for sure why it was E. It could have been that he named it after himself, but it seems more likely that there's probably another reason. At any rate, using E as the way that we talk about this constant stuck. So this number is E. Okay. What's interesting is it's so relevant in logarithms and in calculus. When we do calculus with this thing, it's going to blow your mind, but we're not going to do that today. That's tomorrow. But it is so unbelievably amazing the implication it has in calculus and in doing derivatives of exponential functions or exponential expressions and logarithmic functions and expressions. Like, it's amazing how perfect it is, but that's not even where it came from. That's not its history. It was not developed or discovered because of calculus. Okay. It was actually discovered, I think, I'm not even sure, maybe this may not be a fact, but all the early history of any usage of this or any talk about approximating the value for E has to do with exponential growth and generally has to do with interest. So interest on money that that's in a bank or in a loan or something like that. Okay, and this is the part that you could read a little bit more about and you could look up, and it's interesting. The one way that they discovered E is with this simple idea of, let's say you have $1 in the bank, and after 1 year, if it's got 100% interest rate, then after 1 year it would double. So 100% interest rate per year, after 1 year you'd have $2. Let's say if you know anything about interest, the compounding period is a big part of it. So 100% interest in a year, but I compound it semi-annually. So it's more like 50% twice a year kind of thing, as opposed to 100% a year. You're going to make a little bit more. And if you continue to change that compounding period smaller and smaller and smaller and smaller and smaller, infinitely smaller, then the amount of money that you get after a year would be a multiple of E. It approaches E. That's probably not the best explanation without kind of going into it in a bit more detail, in particular if you don't know anything about um, compounding periods. But that is one of the first, if not the first, sort of place where it started popping up. And once that starts to make sense to you, it's clear. It becomes very clear that it's a very important base. Because of this, it's a very important base in exponential functions, to the point where people would say it's the most important base. So 2 to the x, 3 to the x, 4 to the x, 10 to the x, none of those really matter. E to the x is the one that matters. In a way, that's one way of sort of thinking about it. Okay, so E is a really important number for exponents, really important number for logarithms. We're going to see how crazy important it is for doing derivatives of those kinds of things. And fundamentally, people would say it is the base for exponential expressions or functions. It's the most important one. Okay, that's enough of that. We've learned about this important number E. What we're going to do for the rest of this unit or the lesson today is we're just going to review a bunch of properties of logarithms, and we're going to do them in other kinds of bases, and we're going to do them in base E. Okay, so let's see. For the function y equals log base b of x, where b is greater than 0 and x is greater than 0. Those are the restrictions on b and x. They both have to be greater than 0. They can't be 0. They can't be negative. Okay, we talked about that in MHF, hopefully. So you can go back and look at that. But for now, take my word for it. We're not going to go over all that again. For any base b, so this could be log base 2, log base 3, log base 10. Log base b of 1, well, the way that I can think about this is I can write it as b to what exponent equals 1, because logarithms calculate exponents. The logarithm finds the exponent. And if you remember from MHF, the big deal that I make when you're trying to remember how logarithms relate to exponents, the base stays the same. So this is a base of b, and this is a base of b. The base stays the same, which means the 1 has to go to the other side, and the thing that I'm looking for, okay, is the exponent, right? So b to what exponent equals 1? The answer is 0, right? The answer is 0. Log base b of b, well, that's saying b to what exponent equals b. So this answer is 1. log base b of x to the n. This is one of the properties. This is a really important one. Do you remember what this one is? This is the one where I can bring the exponent down out front. And we already saw how useful it is, and we'll continue to see how useful that property is. So that is equal to n times log base b of x. Log base b of x to the n equals n times log base b of x. I'm going to stop there, and I'm going to move over and do a bunch of these because I should have been doing it all along for base e. This means base e. So if log base b of 1 is 0, this is just like log base e of 1, because ln is just log base e. So this must also be 0. And log, oops, I'm going to do that in a different color. Oh, geez. Is 0, which equals log base e of 1. So ln of e is equal to log base e of e, which equals 1. And ln of x to the n is equal to log base e of x to the n, like we just saw, which is n times ln of x. So same thing. There's nothing special about lns different from logarithms, except they're useful in ways that a lot of other bases aren't. That's what's special. Otherwise, it's a normal logarithm. Okay? Okay. Log base b of b to the n means b to what exponent equals b to the n? Well, it's got to be n, right? So this is equal to n. And same thing here. This is log base e of e to the n, or ln of e to the n is just equal to n. If I have log base b of x plus log base b of y, this is one of our properties. That is equal to log base b of x times y. Remember that one? Okay, if you're adding logarithms, you can take the log of the product of the arguments. And if I'm subtracting, then I get log base b of x divided by y, right? Same thing over here, ln of x plus ln of y is equal to ln of x times y. And ln of x minus ln of y is equal to ln of x divided by y. Finally, this is that strange one, b to the log base b of x. It's actually almost identical to that one, but it's just the exponent version of that. Okay, and so try to remember this one's equal to x, and this is e to the ln of x, which is the same as b to the log base b, because ln is base x. So this is just also equal to x. That one's not going to come up too often, but you never know. Okay. Okay, those are the basic properties. We took several days to learn those and then prove those in MHF, and we're going over them quickly, and we're getting used to the idea of working in base E or ln. I hope that that is at least somewhat familiar, and as you work through the practice over the next few days, that you'll use some of these properties, and hopefully it will refresh and you'll get back in the swing of things. Okay, so quickly, this was one of the most important things we did when we first learned about logarithms, was rewriting an exponential form and getting used to that idea. It's really useful because when in doubt, you can always just rewrite it in exponential form. But it also helps us understand what logarithms are. So the base stays the same, and then the logarithms find exponents. So the thing that it's finding becomes my exponent. And I know that 2 to the 5 is 32. So I can take those three numbers, 2, 32, and 5, and I mean, I can just write them in a way that they are related, right? And I can also do this on my calculator. I can go log base 2 of 32 and get 5. And 2 to the 5 is 32. So I can use my calculator to figure out what the relationship is if I forget it. But hopefully you don't forget it, because that wouldn't be a good start to things. Okay, this is ln of 44 is approximately 3.784. How do we know that? Well, I can just do ln. Notice that my calculator has a dedicated button for it of 44, and I can see that it's 3.784. But what does this mean? It means log base e of 44 is approximately, 3.784. And it means e to the exponent 3.784 equals 44. There's nothing important about that. It's random, but again, just getting used to rewriting it and getting used to working with lns and bases of e. Okay, write in logarithmic form. The base is e, the base stays the same. That means I'm going to be taking the ln. That means this is log base e, base stays the same, of 148.41 will be approximately 5. Okay, but log base e, we don't write it that way. We write ln of 148.41 will be approximately 5. And I am saying approximately because I've rounded going one way. That means I'd be rounding going the other way, right? So if I punch this in, 148.41. I better get pretty close to 5, very close to 5, but not quite 5. Oh boy, what's this next one? Well, this is just practice rewriting radicals in exponential form. So this is going to be e to the 2 over 3. Gives me approximately 1.948, which means rewriting in logarithmic form would be ln, or log base e, of 1.948 would be approximately 2/3, 2 over 3. Ln of 142, evaluate to 2 decimal places. We're just using our calculator here. Calculator should have a dedicated ln button, so I'm just punching it in. This seems fairly simple, but again, we got to take it a little bit slow at first because we're getting used to the idea of working with this number and just getting used to its existence, and finding that button on our calculator. E to the 4. Okay. 54 point, it says 2 decimal places. So 598, ooh, this is a good one, 598, but that's 3 decimal places. So what happens here? Now, the way I think of this, whenever I see a 9, so the 8 is going to be rounding the 9 up. So then I look at it like a 59, and the 59 rounds up to a 60. That's how I think about it. Because what people do is they just do 6, but you need the 0, because if it says 2 decimal places, you need 2 decimal places. And people get confused about, oh, what happens? Like the 9 goes to 0, and then I have to bump the 5 up to a 6. I like to instead think about it as 59 rounds up to a 60. And that always works. I mean, if it was 0.479, then 47 rounds up to 48. Like that is how that works, right? So it's a useful little trick to think about it that way. Okay, so there's 2 decimal places. E to the ln of 12, that's like e to the log base e of 12, so that's just equal to 12. But again, you're going to have your calculator, so if you really wanted to, you could punch that into your calculator. Shift e to the ln of 12. Oops, syntax error because I need a bracket. 12, right? But it is one of those properties, and ln base e of 61 is like log base e of e to the 61, so this is equal to 61. Again, I could check that on my calculator if I wanted to. Ln shift e to the 61. I probably don't need a bracket there, equals 61. Solve for x to 4 decimal places. Okay, so these are little equations, and one of the hard parts about the logarithm stuff is there's all different kinds of little equations depending on where the x is. Sometimes you want to rewrite in exponential form, sometimes you might not. Sometimes you have exponential form and you want to rewrite in logarithmic form. Like it's always different, right? So in this case, I do want to rewrite in exponential form because x will equal e to the 10. The base stays the same. The base was e, and 10 is my exponent. And then I'm just going to go e to the 10. And that gives me x being approximately 22,026, 4 decimal places, 0.4658. What about this one? Well, when I have x in the exponent, I want to rewrite in logarithmic notation. And my base is e, base stays the same, so this is going to end up being 3x equals ln of 50. This is just this idea of rewriting like we did up here. Okay, it's no different, right? Rewrite in log form. And how do you know to do that? Well, a little bit of experience. When you've got x in the exponent, probably you want to rewrite it in logarithmic form. So then I've got x equals ln of 50 over 3. Ln of 50 bracket divided by 3 gives me approximately 1.3040. And finally, if you want to go ahead and beat me to this one, go for it. So this is another one where I am going to rewrite in exponential form, and I end up with 2x equals, the base stays the same, so the base is e to the 1.1. So x is e to the 1.1 over 2. And that looks like 1.5021, rounded up to a 1. All right, so there's a few simple equations, logarithmic and exponential equations that we solved by rewriting. Now let's take a look at another type. We're going to look at a couple more different types. And do we remember these ones? This one's already kind of set up for us. We did these with logarithms, and they might have had different bases. But in this case, I'm log base e, so ln, and this is already set up as the product of two things equal to 0. So I can use, the zero product property, and I can say, therefore, ln of x plus 2 is 0, or ln of x minus 3 is 0. Okay. And that means ln of x equals -2, or ln of x equals +3. And then we start to think, oh, we're going to get exact values of these, by the way. Then we start to think, well, hold on, I thought you couldn't have a negative when you do a ln. Well, if you go back up and you look at those restrictions, and you remember what the restrictions are, that's a good thing. The restrictions of logarithms are that the base can't be negative and the argument can't be negative. Well, the base is e and the argument is x, okay? So x, it's true, has to be greater than 0. And same thing here, x has to be greater than 0. The base has to be greater than 0, but the base is e. That is greater than 0, so we're fine with that. But we're going to find that they are greater than 0, so that's not going to be an issue in these. So that you can have a logarithm or a ln that evaluates to a negative, that's fine. Remember, this is the exponent, and we can have negative exponents. Those are fine. So but if you're ever in doubt, rewrite it in exponential form, and you can decide whether it makes sense or not. So the base stays the same. This means x equals e to the -2. Well, that's fine. That means x equals 1 over e squared. What's e squared? I don't know, it's just e times e. 2.7 times 2.7, right? And then 1 divided by that gives me this answer. I'm supposed to do exact value, so I'm leaving it. That looks like an L, so I'm going to fix it. And that would be my answer as a decimal, but that's fine. I'm done. And this one's going to be x equals e to the 3. So this question had two answers, both fine, no worries there, okay? And I think this is something that people mix up where they start to think that, oh, therefore no solution. No, this has a solution just fine. So be very careful saying no solution when there is a solution. If you're not sure, or if you're making mistakes with that, take it all the way and evaluate it. When you rewrite it in exponential form, it won't make sense if there's a negative in there, hopefully, and you'll be able to catch that. Okay, you'll have a negative in the base or something like that. All right. What about this one? How would we do this one? Well, this one's not factored yet. It's already equal to 0. It's not in factored form though. So this is like a squared minus 3a minus 10 equals 0. And that is something I can factor. So this becomes, you can factor it like this if you like, on separate paper or something like that, or just think about it in your mind. Two numbers that multiply to 10 and add to 3 or have a difference of 3. So those are going to be 5 and 2. So I'm left with ln x and 5 and ln x and 2. And I want the 5 to be negative, so I get the negative 3. So therefore, ln x equals 5 and ln x equals negative 2, which means x is e to the 5 and x is e to the negative 2, or 1 over e squared. There was nothing in the question that said I couldn't have negative exponents. I'm doing that just because it's a habit, it's a good thing, it's a common thing. You might see that, no negative exponents allowed, something like that. It's not really what we're doing in this unit, okay? But just reminding us, really the biggest reason why I'm doing it is to remind us that negative exponents are fine. It's just a fraction, right? It flips the base. So it doesn't mean there's no solution or something like that. People might stop and say there's no solution, so that's not true, okay? All right, let's see, we got two more, and they're really cool little questions. And I usually like to stop here and see if anybody knows what we can do or sees what we can do to solve this question. So you can pause and think about it for a little bit if you want. But hopefully you noticed that I can common factor out an e to the x. Okay, and I'm left with that. So therefore, e to the x equals 0. And x cubed minus 8 equals 0. Well, x cubed minus 8, that's a difference of cubes, but the easiest way to solve this, I'm not going to do the whole factoring thing there. My goodness, why would I bother doing that? Cube root of 8, x is 2. So there's one solution there. Okay. What about this one? Well, this is where our knowledge of the graph is very useful. So I'm going to go down here and I am going to sketch any exponential function, but let's say this is y equals e to the x. When does y equal 0? Never. There's an asymptote there. It never equals 0, right? So there's no solution to this, and I can tell that by the graph, because e to the x or any exponential function never hits 0. It has to be greater than 0. That was our restriction, okay? The other thing I could do is I could rewrite this in exponential form. This is x equals ln of 0. And I could use my calculator to calculate that. Oh, let's do the ln of 0. Oh, right, you can't. Okay, so this has no solution. But the other part does, where x equals 2. So this question, there's a question where you do have an answer that's not an actual answer, okay? And you would say no solution. Let's see, whoops, we got one more here. This one's cool as well. It's got a little trick to it. Again, if you want to pause and think about what this trick is, that would be fine. That'd be a great idea. You may never have quite seen something like this in grade 11. You may see things kind of similar to this, but they are tricky, and I can imagine some people it never quite clicks for them. It comes down to my understanding of properties of exponents, exponential expressions. And can't I rewrite this as e to the x all squared? Because a power of a power means I multiply. So it would be e to the 2 times x. But I can split that up into any way I want. E squared to the x or e to the x all squared. And e to the x all squared is the one that I want. Because the way that it works is anything squared plus the same anything, that's that trinomial form. This is like a squared plus a minus 6 equals 0, where a equals e to the x, right? And so now I can factor that, and it works out to e to the x plus 3 and e to the x minus 2 equals 0. Okay, so 3 times negative 2 is negative 6, and 3 minus 2 is positive 1. So therefore, e to the x equals negative 3, or e to the x equals 2. Rewriting in exponential form, or sorry, in logarithmic form, that means x equals the ln. So base stays the same. It was base e here. So it's still base e, log base e, which is ln of negative 3. And x equals ln, again, base stays the same, of 2. Well, again, using my calculator, I can do ln of 2, and that works just fine. Ln of negative 3 absolutely does not throw us an error because, again, by the graph, there's a restriction there. The argument of a logarithm has to be greater than 0, so this one has no solution. So therefore I have one solution, and it's the ln of 2 if I'm doing exact value. Okay, so there was a little bit of a warm up for solving some equations, a reminder of some of the logarithmic properties, rewriting in logarithmic form and rewriting in exponential form, and this introduction of this new number, this really important new number. It's the last sort of big step into a new world in high school math that we do. I mean, we're going to do vectors, which is a sort of a step in a different direction for math, absolutely. But to me, this is like, learning about E is the same as learning about pi, learning about I. It's a pretty big deal. And we will see why it's a big deal for calculus, but like I said, it's a big deal in a lot of other areas, generally related to exponential growth and that kind of thing. If you are not confident with your understanding of the language of logarithms, then you've got to go back and practice that and brush up on that and get better at that. Have to, have to, have to. It's so important that you can easily rewrite a logarithm as an exponent, and same thing, an exponent as a logarithm, and that you can go back and forth, and hopefully you get back into the habit of thinking in logarithms, and you don't always have to be converting back and forth, but that converting is a good place to start. But just in general, I think before we go too far into this unit, you want to be comfortable working with logarithms again, right? So at least as comfortable as you were last semester in MHF, if not more so. If you were good at that unit in logarithms, you'll probably just need a day to brush up. If there was anything about that unit that you didn't like or didn't click for you, then you may want to do more work going back and reviewing it, okay? We are going to do a couple of days of derivatives. And then we're going to start using them. So we don't have too much time, but you do have a bit of time. Okay, good.